Hey, it's your boy Chili here. Welcome back to Shared Memory. In this video, we're going to learn mostly about how virtual memory works, especially with respect to sharing memory between processes. So this is going to be a little bit more on the operating system memory management side of things, and if you're interested in that, then I would recommend you to stick around. In the last video, what we tried to do is we tried to write a pointer to shared memory that's pointing to another place in shared memory, and then access that memory from a client. So use that pointer to read the place in shared memory that it points to. And that caused an exception. And I asked you, well, why do you think this is? Why do you think we have this problem? And, you know, there's a couple of avenues to pursue here, right? Number one is, well, there's a problem with the actual sharing mechanism and the way we're using pointers. But another one that you should never rule out is I set it up wrong to begin with. You know, my pointer that I wrote was bad from the beginning, so no matter where I read it from, it's not going to work. So in order to test that, I added a little bit of extra code in here. So in shared memory, I added to the server the same function getString pointer that we have in the client. And so the server is going to read that pointer in shared memory and use it to access the string in another place in shared memory. And in my companion app here, what I'm going to do is instead of putting out go ahead, I'm going to put out whatever is in that memory. And then in my test here, first of all, I'm not going to check to see if it's go ahead, because it's not going to be go ahead, it's going to be something else. But down here, what I'm going to do is when I read in the ACK from the companion, I'm going to use that as my expected string. I'm also going to write it out so I can see what it is in the test output. So if we run the test with that, we still get an exception. But in the output, we can see that the expected string that was output from the server is the correct string. It's not a bunch of garbage. The server didn't crash when it tried to access the pointer. And it got the correct data. So that means there's nothing wrong with the pointer itself in the shared memory. From the server process, it works fine as a pointer. But from the client process, when we try to access it, we get an exception. Now, in order to understand what the problem is here, we got to go back. We got to understand how processes live in memory and how that all works. So a naive interpretation that I think a lot of people have, if they have any sort of inkling of how, programs live in memory, is you think, well, I got my program, like program A in here, and then I got like program B in here, some other place in memory, and then maybe the operating system lives here, and all my programs are living in memory. They're accessing their own locations in memory. If you have a little bit more of a sophisticated view, you might think, okay, so the OS is actually protecting other pieces of memory. So A can't access this address, it'll cause, an exception because it's being protected. A can only access what's within its region. Now, this is a complete fabrication. This is a fairy tale. This is not how it works in modern operating systems. This is how it works back in like DOS when you're working in real mode. But we work in protected mode. It's completely different. So this is the actual view that every process has. Every process believes it is alone in the universe. It's living in a vast void, right? If it's 32-bit, then this is like a 4 gigabyte memory space. If it's 64-bit, then it's significantly more than that. But whatever the case is, every process feels like it's the only one in here. It's a very lonely existence. I don't know if processes are capable of having like an existential crisis, but I think this would probably induce one. But at any rate, they all feel like they are in their own space of memory. They have the run of the kingdom. Now, thing number 2 to understand about memory is it's broken up into chunks called pages. And these sizes, it depends on your architecture and your processor and everything, but typically on Windows, on Intel architecture, it's going to be 4 kilobytes. So every 4 kilobytes, that's another page. And so the way it works is Windows manages a big pool of these virtual pages, and then it maps them to virtual addresses in the application's process spaces. Mapping them like this. And you might think to yourself, well, okay, Chili, that makes sense. You're going to map places in the application process space, and then these are all just every one of these pages is just set to be a fixed address in RAM, and that's how you allocate RAM to your different processes. And no, that's not how it works either. It's actually even more complicated and more flexible than that. So say this is your RAM, we can divvy it up into 4 kilobyte sections, just like we divvy up our virtual process spaces. And then we can map these pages to places in RAM, but we don't have to map them contiguously. We can map one over here, we can map this one over here, we can map this one here, we can map this boy up here in between, and it's all good. So you have freedom on both ends for these pages. You can map them into anywhere you want in the virtual process space, and then you can map the other side to any physical place in RAM. And then what happens is when the application, it's going to do some stuff, it's going to try to access some memory here. The operating system is going to check into a table, and it's going to, say, okay, so the address that they're trying to access, that corresponds to this page, and this page corresponds to this place in RAM. So we're going to take the offset into the page that they use there, offset into this piece of RAM, and load the memory at that location, and that's what we're going to return. I say the operating system, but it's actually like it's hardware accelerated by the CPU with lots of caches and everything, so it's typically super fast. Now, what happens when an application tries to access memory that hasn't been mapped into their space yet? There's no page that's been mapped into that location in their virtual memory space. Well, the OS, the CPU, is going to do a lookup, try to find the page that corresponds there. There is no page. I mean, that's a segmentation fault, basically. Your process does two things. It shits the bed, and then it dies. So don't do that. I think we're all, we're pretty familiar with that phenomenon. Now, there's a number of advantages to this virtual memory system. Obviously, process A can't get at process B in no way. Like, even if it knows that, okay, process B, its stuff is at this address. If process A tries to access that address in its virtual memory space, it's not going to map to any pages. It's not going to go anywhere. So there's no way for process A to get at process B, generally. The other huge advantage is that these pages, they can map to places other than RAM. So imagine process A needs to grow its heap. It's going to grow it by, 2 pages for whatever reason. So we need 2 more pages that the OS is keeping track of. And they're going to map them into the virtual memory space of process A right here. So we're going to map this one into here in the RAM. And oh no, our RAM is full. I guess we're just going to crash the program. Well, no, we don't have to do that necessarily. What we can do, we could map pages to another place. We could map them to a file. We'll call it the swap file. And so we'll map one of those pages into here. And so typically what happens is you got some stuff mapped into the swap. When the application tries to access that page, it's going to go here. It's going to say, that's mapped into a file. We want to be working with that. So we're going to have to move that into memory. So we're going to pick one that's in memory. And we'll say this one. No one's been using this one for a while. Doesn't seem that important. So we're going to unmap it. We're going to copy it into the swap here. And then we are going to copy whatever's in the swap here. We're going to swap that into this location here. So now this one maps into this memory here. That's why it's called the swap file, because you're swapping in and out of RAM as these things are needed. It does an access. It does something called a page fault, which triggers the OS to swap the memory in here, put this page resident in RAM now, and then the program can proceed. So it's not a good thing when you do a page fault, but it happens. If you're oversubscribed in your memory, your applications are using more than you have physical RAM, but it's better than your OS just crashing. And now we come to another powerful feature of this system. So you can freely map from pages into the virtual memory of a process. And that's not just one-to-one. You can map the same page into 2 different processes. And that is what we're doing when we're using shared memory. We're just taking the same page. It's going to be mapped, typically into some place in RAM on this side. But in this side, it maps to 2 different processes. So if this process accesses this address, they get this place in RAM. And if this process accesses this different address, they get this same place in RAM. And so they can share memory. I'm going to move the mapping a little bit for the purposes of this next demonstration. So let's say that it maps up here now. These two map to the same memory. They see the same values. Now let's say that process B puts a pointer into this shared memory here that points to the beginning of the shared memory. And they can write that pointer in there. They can use that pointer to access this location in a shared memory. All works fine. That pointer is also visible from process A. What happens when process A reads the value of that pointer? Well, it's the same value for both of them. So it points here in process B. So it points approximately here in process A, like a little above the middle of the process, in the memory space, which maps to nothing because it's the same absolute pointer value, but the shared memory segments map to different locations in the memory spaces of these different processes. In general, your processes, your programs are going to start off in different locations in their virtual memory spaces, and you can't really fully control where everything is mapped into. There are ways of controlling it to a certain extent, but sometimes a previous thing is mapped into the location that you want to use. So you can't do that. You can't depend on mapping pages into the same location in every process. You have to deal with the fact that they're probably going to be in different locations. And that means that your absolute pointers aren't going to work because they're going to be pointing off in no man's land. And that is exactly what is happening here. The pointer, which was valid in the memory space of the server, is not a valid pointer in the memory space of the client because the shared memory itself is located in a different place in memory. Now, this has a lot of pretty important implications on how we write applications and how we put data into these memory spaces. So, I mean, the first big one is, okay, so you can't write any, raw pointers in there and expect them to work because they're not going to work. So what else does that mean? Well, a big one is no virtual functions, because virtual functions in most compiler implementations require pointer to a function table of functions to call, and depending on the concrete type of the class, it's going to point to different tables. Well, that pointer is stored with the object, and it is, an absolute pointer. So when you store an object in one process with a virtual pointer, it has virtual functions. You try to access it from the other process, it is going to crash. So no virtual functions. That's a pretty big limitation in C++. What else you got? Well, no containers, std, string, vector. No. Why? Two reasons. One is fixable, one is not fixable. So the fixable reason is that by default, std basic string, uses an allocator that puts the string data itself on the heap, which is not going to be in your shared memory. So even if you construct a string in the shared memory, it is going to own data that is not in the shared memory, and so the other process won't even be able to see that data. But you could give it a custom allocator that puts the data in the shared memory itself. But the second problem, and the one that is not fixable, is that std string uses just basic ass raw pointers, absolute pointers to memory, and so that's a non-starter, right? We can't use those. The same with vector, same with basically any container in your standard library implementation, typically. They're all just going to use your simple C raw pointers, and those aren't going to work in shared memory. So, no storing pointers, no storing references, no storing containers, and no virtual objects, no classes with virtual functions. So that's a lot of limitations on what we can do with shared memory. So how do we get around them? We can get around some of them. So what are we to do? Well, first of all, we can store our pointers in a different way. We can use a little bit of a smarter, kind of exotic pointer type that will enable it to be usable from any process who is sharing the same memory space. And the way we do it is we use offset pointers. So this pointer does not store a direct absolute address to the thing that it is pointing to. No, what it stores is it stores an offset. So a number of bytes from some point of reference. Now, one point of reference you might think of is, okay, so the start of the shared memory. So I could store a pointer that is an offset, it's like, just go 69 from the start of the shared memory, and that will get you to where you want to be. And that's pretty good, except that now, every time I want to access this pointer, I also need the extra information of what's the start of my, shared memory, which every process knows. It has to know where the shared memory begins. So this is possible, but it's a little awkward. If every time you have to access a pointer, you have to pass it also in another pointer to the beginning. So there's actually a much more elegant way of handling the problem. Whenever you access a pointer, you already know the address of the pointer. That's the thing you're accessing. So what if you make the offset relative to the address of the pointer itself? So instead of this being 69, it's actually negative 420. And that way, you don't have to pass in another parameter, because when you access, an object in C++, you innately have this pointer. And you just say, okay, add the offset to this, and that's where you're pointing to. So you basically make a smart pointer, a class, where when you dereference it, it is going to add an offset to this to get you to where you're pointing to. And that's all an offset pointer is. And if you do pointers with offset pointers, then you can use pointers in shared memory. And if you use offset pointers for your string container with an appropriate allocator, you can have a string that lives in the memory. Now, I don't think we can get around the virtual memory problem, the virtual function problem. That's just a non-starter, because that's the way the compiler works innately. Not all compilers, by the way, need to use a virtual pointer to a table. And I believe Clang doesn't use one. But most of the ones I'm aware of do use one, so it's not really feasible. And it's also an implementation detail, so it's something that, I don't know, depending on how the binary compatibility is defined for the compiler vendor, might change. So it's not something you could depend on. But regardless, we can have pointers and we can have containers. And that opens already quite a bit of possibilities. So the next question is, okay, so how do we use offset pointers? We could write our own, but I showed you Boost for a reason, because it already has all of this stuff written very well. Many, hundreds of programs use it in production. So it is tried and it is battle tested, and it's the industry standard. So let's use it. So because we virtualized and encapsulated things properly, we should not need to change anything about the way our tests run. We just need to change the internal implementation of our shared memory classes here. And that's always a characteristic to strive for in your code. So we just need to change the mechanism that we're doing in this implementation file here. So the first thing we need to do is, instead of creating a normal pointer, we need to create an offset pointer. So we do bip. Let's see if I can find offset pointer. Hopefully it's already in there. I don't have to include anything. We want an offset pointer to car. It says incomplete type. That makes sense. So we include boost.interprocess offset pointer. That should make you happy, and it does make you happy. So we can create an offset pointer, give it a raw pointer, and it will convert that into an offset relative to this pointer, where this pointer sits in memory. Hopefully that is the way it works. Okay, so let's figure this out. So we're going to place this car pointer with an offset pointer to car, but that breaks the interface. So this is already telling us that this isn't the way we want to do things. So we're not going to do that. Instead, what we're going to do is we're going to reinterpret this as a pointer to an offset pointer. Now there is no conversion from interprocess offset pointer to const car pointer, but function called get, which gets the raw pointer from that path. And then we can add const, because it's free to add constants. It only costs you when you want to remove const. So that's fine. So here we are accessing it now as just a raw string pointer. And now the other functions work fine. So that's all we need to change. And then we could probably just copy pasta this one down into here. Except that we need to do server, because this is defined within the scope of the server. But this will get the same offset pointer at the same place in shared memory. And when we call get on this one, it's going to be converted into an absolute pointer in the memory space of the client. And all the other functions should work the same. So first things first, we try to compile. We see what we missed. There's templates involved, so it's often something, but today it was nothing. And then the second test. Well, let's just see if we didn't break any of our other tests. I like to leave the tastiest one for last. Keep the suspense up. We didn't break this one. We didn't break this one. All right. Moment of truth. And it works. It works. We got the expected string. We can now read from both. There's no seg faults. Nobody shits the bed. Nobody dies. And I mean, let's look at the butcher's bill. We changed one file. We replaced this car pointer with an offset pointer. We replaced this one with an offset pointer. And we did the same down here. That's all we did. And we had to add the get on the end here. Had to add that get. And that, my friends, is how you do pointers in shared memory with boost.interprocess. It's pretty painless. It is pretty elegant. And it allows you to do bigger and bigger things. But that's going to about do it for this video. In the comments, I want you to tell me, if you've made it this far, are you interested in seeing a little bit more about what boost.interprocess has to offer? Because this is only the very basics. There's actually a lot more powerful stuff that, like, you could put full containers into memory, like strings and vectors and maps. And you can give things names so that can be easily found by all process. You can dynamically allocate and deallocate in the shared memory like a heap. Lots of interesting things to look at. But I'm wondering if anyone is interested. I might do a couple more videos on this topic in the future. If nobody's interested, then that's fine too. I might just drop it, or I might make videos anyways, because I'm doing this a lot in my day job, programming C++ in the trenches. This is the kind of thing that I'm doing, except at a far larger and more complex scale. So because that's the headspace I'm in right now, that's kind of why I feel like I want to share it. But let me know what you think, if you're interested at all in this kind of low-level systems programming kind of thing, or if it's just not really something that you're into. But until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, helps a lot. And I will see you again with some more C++ shared memory.